Hey guys, Rao this side. Welcome to Get Conqueror channel. And here, by end of this discussion, you are going to get clarity about few things like kind of KCL, KVL. KCL, basically our networks is in a box. What is that box? Outer layer is for linear, lumped, passive, bilateral, causal, time invariant systems. Now, our KCL, KVL, can we apply to nonlinear circuits or not? Can we apply to unilateral circuits or not? Can I apply to infinite systems also or not? Okay, so KCL, KVL boundaries we are going to fix in this particular session. And the next thing is two-terminal systems. Okay, in two-terminal systems, once we analyze two-terminal systems, we are going to conclude that all of our active elements are not linear. Okay, all of our active elements are not at all linear. But how dare we to use non-linear what do you say sources, active elements, non-linear active elements in the linear time invariant systems of network theory. Okay, so what we say we discussed about we discussed about active elements, passive elements. Passive elements are anyway linear. We don't have any doubt about it. Okay, but if you think of active elements are non-linear. But though they are non-linear, how can we use them in our network analysis? Because network analysis is meant for linear systems at least. Okay. Before discussing all this, let me share details about myself. I'm Rao, and by GATE 2021, I completed 20 years of teaching for GATE and ESE aspirants because I never taught in engineering colleges. I started taking classes in GATE field only. Okay. And subject statement, if you see, I taught machines, networks, and power systems. In this platform, depending upon the time availability and all, I will start power systems also. And then please like the session and share the session to your friends such that we'll get motivation. It means I also should be motivated to do more and more videos like this. Now, yes, if you want to make me part of your preparation, use KNR 10. And here in Unacademy, there are two kinds of paid platforms. Plus platform is there and Iconic platform is there. In Plus platform, you are going to get live classes, crash courses, rank improvement batches. Where is this? Yeah, rank improvement batches. And you can study both in English and Hindi also. And doubt solving will be there, weekly test will be there. This is about Plus subscription. If you want Iconic subscription, which is super set, okay, which is better, you are going to get one personal coach to whom you can share your demotivation or kind of problems and all. He will understand because he is an achiever of your age band. And study planner he is going to prepare, and personalized test analysis, which is very important because critically we have to analyze the test. Otherwise, we don't come to know our weaker areas. Okay, and study materials also they are going to provide in Iconic subscription. And if you come to what do you say this Plus subscription, paid subscription for 12 months, it is going to be 27,225 after KMR 10 after getting 10% discount. And for 18 months, it is going to be 34,650, and for 24 months, it is going to be 39,600. Now coming to Iconic subscription, for Iconic subscription for 12 months, it is going to be 40,500, and for 24 months, it is going to be 54,000. And no cost EMI facilities are available. And they thought of increasing the fee structure from July 1st, but they postponed that because of huge demand from the student community not to increase. But anytime soon they can increase. So if you want to subscribe, try to subscribe soon. And one more thing is like at least now we have to start the preparation. And there are Spark and Vero batches only for English speaking guys who cannot understand Hindi. Like of course I can understand, but okay. Now Spark batch is meant for GATE 2022 and Vero batch is meant for GATE 2023. I'm going to start electrical machines in this batch. And all these faculties I worked with, okay, means Vishnu sir, Rajesh sir, obviously top faculties of India are working now with Unacademy. And see here, this is lecture batch or Arohan batch. This is meant for GATE ESE 2022 lecture batch, and Arohan batch is meant for GATE ESE 2023. Obviously, well-known faculties, Ankit Goyal sir, Suresh sir, Bhimshankar sir, Vishnu sir, okay. And here they are going to start the batch from 14th July, okay. And this is about test series. Once you pay, they are going to conduct test series also, which will be definitely of use for you. And if you want to follow me in Unacademy app, follow me at Rao for you, such that whenever I come to special classes or kind of plus classes, you will be getting notifications and all. Now, let us start our discussion. KCL, KVL. Okay, first I'll start with KCL, KVL, and then I will enter into kind of two terminal systems. Okay, in KCL, KVL, let me start with KCL, and we are going to connect this with duality also, because in KCL, if I take entering currents as positive, and in KVL I should not take voltage drops as positive. Means there is some interlinking mechanism, because whenever we are going to deal with duality, at that point only duality should not be discussed. Actually, we have to start from starting only. Okay, so means in order to maintain duality, there is some interlinking mechanism between KCL and KVL. Means in KCL, which type of currents has to be taken positive. As per that, we are supposed to take voltage drops or voltage rises as positive in that way. Okay. Now, let me think of about KCL. KCL, actually, this is Benjamin Franklin. Spelling can be wrong also, Franklin. As per his proposal, charge is also conserved. Charge is also conserved. Okay. Kind of, if I think of one water tub, if I fill this with water, and this particular water magnitude or volume of that particular water is going to be considered. Now, for example, if I have some tap here, just like that. If I have some tap here, and if I open the tap and if I take out some volume of water, this particular volume of water will be reduced by the same amount. Conservation of water. Similarly, means he proposed for conservation of charge also. For example, if I have charge accumulated here, and from this charge, okay, let us think of this charge is accumulated here. All over the charge is accumulated, some magnitude of charge. Okay, if I take out some charge, remaining charge is going to be existing there. That's it. Okay, charge is also going to be conserved. Now let me tell you here. Complete network theory is based on two conservations. One is conservation of charge and another one is conservation of energy. Okay, conservation of energy in KVL already we have seen. It means just for formality we are going to write some kind of equations now. That's it. Okay, means again let me tell you, because when time constant is going to become zero in kind of in transients. Okay, then you will get the clarity about this. Okay, when time constant in transients is zero, then what is going to happen? I'm going to raise this particular discussion at that point. Now, fundamentally, complete network theory is depending on two conservations. One is conservation of energy and another one is conservation of charge. Conservation of charge will be given by KCL. Conservation of energy will give you KVL. That's it. Okay. Now, see here. Let me define a node first. Okay, what is meant by node? Means node will not have any properties of its own. Node don't have any properties of its own, because kind of resistance, it is having its own property. Inductance, mutual inductance, capacitance, they are having their own properties. Okay, if node is having some kind of its own property, would have included that in basic properties, right, or basic elements. Node does not have any basic property of its own. Rather, it's just an interconnection of two or more elements. Okay, so this is going to be interconnection of two or more elements. Of two or more elements or properties, we can say. Right, that is nothing but the node. At the node, the moment node does not have any of its properties, any of its own properties, meaning that node cannot store any kind of charge. Okay, let us think of, I have a node. Okay, let me think of this is a node. Upon this node, it is connected with maybe various elements. Let me connect here inductance of network inductance, which is linear. Let me connect non-linear. Non-linear in the sense we are going to show just two lines there, such that indirectly I am saying that this particular inductor is made from core. It is actually having the core. Upon iron, we are going to wind. This particular thing we cannot analyze in network theory. Rather, we are going to analyze in electrical machines. So this is non-linear. And let me think of here resistance, which is linear. Okay, and let me all these 1, 2, 3 elements are bilateral. Now let me think of connecting unilateral also. Let me think of connecting a current source here. Let me think of connecting a, why to take independent? Let me take dependent. Some 3ix. That ix, let me consider here. Okay, so this is going to be the system structure. I can have voltage also. I can have some voltage source also connected in between. Now, this is the nothing but the node, right? So, this particular node does not have any of its properties of its own, meaning that it cannot store charge. Okay, for example, if I think of capacitance can store charge. That is its own property, but node does not have any kind of property of its own, meaning that it cannot store charges. Now, let me think of currents. Okay, for example, this current is flowing in this direction I1, and this current is coming in this direction I2, and this current is going in this direction I3. This current is coming in this direction I4, and this current is coming in this direction I5. I5 is nothing but Ix. Okay, and this current is flowing in this direction I6. I6 is nothing but 3 into Ix. Ix is nothing but I5. So I6 is going to be 3 into I5. It is going to be calculations we will see later. Because calculations we are already mathematicians. Okay, calculations what is actually simple. Okay, now for this, let us write KCL. What is KCL? The moment charges are going to be conserved, meaning that it cannot be stored at this particular point of node. Meaning that whatever will be the currents entering at a particular node should be equal to leaving currents. Okay, so means current cannot be stopped here, or charge cannot be stored at this particular node, meaning that entering currents equal to leaving currents. That's it. Okay, but see here, conservation of charge. Okay, forget about conservation of charge. Let us think of conservation of power, conservation of energy. Okay, so conservation of energy, will it be decided by linear, non-linear? No, because it's nature. It's nature, right? So for linear also conservation of energy will be there. For non-linear also conservation of energy will be there. Okay, conservation of energy is everywhere. Okay, and conservation of energy is going to be equally applicable for distributed parameter model also or for lumped parameter model also. Getting the point, right? Maybe for distributed parameter model, you may not know how to apply that, but conservation of energy will be everywhere. Because our fields, electric field, magnetic field, kind of gravitational field, these fields are conservative fields. Okay, so the moment conservation of energy is valid, KVL is going to be valid. KVL, voltage law, is going to be valid. Similarly here also, means we need not bother about this is linear, this is non-linear, this is unilateral, this is non-linear, this is linear. Some kind of stuff we need not bother. But of course, we are going to use this particular KCL in our linear time invariant system or linear lumped passive bilateral causal time invariant systems. We are going to use. It doesn't mean that we cannot use KCL in non-linear. Okay, machines non-linear. Machines non-linear. Okay, but we are going to apply KCL there. We are going to apply KVL there. Okay, so point of conclusion is very simple. KCL, KVL is going to be valid in all systems. Okay, but we may not be able to apply in some situations. We are going to discuss. Anyway, means currents entering equal to currents leaving. Or we can say algebraic sum of currents entering at a particular node equal to 0, or algebraic sum of currents leaving at a particular node equal to 0. Okay, let me see these three statements, and after that, my sections in KVL I don't take much time. Now, let me think of currents entering equal to currents leaving. Okay, so currents leaving, maybe let me start with currents entering. Okay, so currents entering I2, current leaving I3. Okay, I2, I3, I4, current entering, current leaving, current leaving, current leaving, I1. Okay, so this is going to be the KCL equation. This is going to be the KCL equation. Currents entering equal to currents leaving. Or in another way, because you may think that equations are same, but it is not like that. We should follow one system such that we will be able to understand duality in a very easy way. Now, let us think of algebraic sum of currents leaving at a particular node equal to 0. If I see I6 is leaving, it's fine. I5 is leaving, it's fine. I4 is entering, or I can say minus I4 is leaving. What do you say? Okay, I means if I say algebraic sum of currents leaving at a particular node equal to 0, I6 is leaving, I5 is leaving, I4 is not leaving, rather minus I4 is leaving. Okay, or I can think of algebraic sum of currents entering at a particular node equal to 0. So algebraic sum of currents entering at a particular node equal to 0, meaning that I4 is entering only, I5 is not entering, but rather minus I5 is entering. Okay, out of these three, let me consider one as standard. Okay, we are going to follow the same way. Currents entering equal to currents leaving we can use. Our algebraic sum of currents entering at a particular node equal to 0 we can use. Our algebraic sum of currents leaving at a particular node equal to 0 we can use. In that, let me use the third statement. Algebraic sum of currents leaving at a particular node equal to 0, I'm going to use. Okay, if I use that, start from I1. Algebraic sum of currents leaving at a particular node equal to 0. So I1 is leaving or not? Yes. I2 is entering. So minus I2 is leaving. Plus I3 entering, leaving. I4 is entering, so minus I4 is leaving. I5 is leaving, it's fine. And I6 is leaving, it's fine. And equal to 0. Equal to 0. So we are going to standardize this. Okay. Algebraic sum of currents leaving at a particular node equal to 0, we are going to follow. And we can say that KCL can be applied to equally to all. Okay, let me tell you about that also. For example, for lumped parameter model, okay, for lumped parameter, conservation of charge is going to be varied for lumped parameter model also, distributed parameter model also. Okay, so let me think of lumped parameter model. Okay, so this is going to be lumped parameter model, or maybe let me think of kind of transmission line model. Medium short transmission line model, kind of. Okay, so can I apply KCL here? Yes. Can I apply KCL here? Yes. This is lumped parameter. But with distributed parameter, definitely we can use. With distributed parameter model, definitely we can use. But I don't know how to use. Okay, kind of. If I have resistance, inductance, capacitance. Resistance, inductance, capacitance. Resistance, inductance, capacitance. So this is going to be infinitesimal, right? So this will be extended to infinite. Distributed parameter model. So the moment it is a distributed parameter model, how to identify this is a problem. So rather than that, of course, we are going to develop some other ways of solving this, but we can apply here, but we cannot apply here. Because in distributed parameter model, we cannot touch one node. That's why in distributed parameter model, means mathematically we are going to convert, and with that we are going to do. Okay. Anyway, let me think of Kirchhoff's voltage law. Okay. Already we know Kirchhoff's voltage law is derived from conservation of energy. Okay. Let me have a small recap of whatever we discussed previously. So this is going to be Q. And my electric field is going to be like this. Right? Electric field is going to be like this. Now, I'm going to keep one small test charge here. I don't discuss everything, okay, but small thing. Now, if I keep one test charge here, small test charge here, okay, some repulsion force will be there, some attraction force will be there. Sorry, applied force will be there. Now, you are moving this particular charge from position 1 to position 2. You are moving your charge from position 1 to position 2. You are supposed to expend energy or not? Yes, because opposition is there. Beyond opposition, you have to push your charge from here to here. You push, for example. Okay. So while pushing the charge from 1 to 2, you expended energy. From 2 to 1, it is going to deliver energy. Such that if I move my charge from here to here, you have to expend energy. If you move back the charge to its original position, it is going to deliver energy. Expended energy equal to delivered energy, conservation of energy. Okay. Now, if I follow this closed path, if I come back here, what is the net amount of energy? 0. While moving from here to here, this is going to be higher potential, this is going to be lower potential. While moving from here to here, -2 plus voltage rise. While moving from here to here, in this direction, +2 minus voltage drop, +2 minus voltage drop, -2 plus voltage rise. Voltage rise is equal to voltage drop. Okay. Our algebraic sum of voltage rise is equal to 0. Our algebraic sum of voltage drops will be 0 in any closed path independent of the path followed. For example, rather than this path, let me consider it's my own wish. Okay, so energy will be expended, delivered, because it is moving away from the main charge. It is going to be delivered and expended. Such that from here, because our field is conservative field, so from here to here means whatever may be the path you chose, okay, independent of the path followed, maybe I may move the charge here or I may move the charge here, independent of path followed in any closed path, voltage rises equal to voltage drops, or energy expended equal to energy delivered. That is the concept. Okay, now let us think of system. Okay, electrical system connected with many properties or many elements. This is the system. Okay, this is going to be a closed system. Now, if I start from here by carrying 1 coulomb of charge, for example, if I move from here to here, I'm going to start from here. I'm going to start from here. So from here to here, to here to here, to here to here, to here to here, in any closed path, independent of the path followed, in any closed path, voltage rises equal to voltage drops. Okay, or algebraic sum of voltage rises is going to be 0, or algebraic sum of voltage drops is going to be 0. Now I'm going to standardize voltage drops. Okay, basically in our KCL, currents leaving we have taken it as positive. Okay, currents leaving from the node we have taken it as positive. So here we are supposed to take voltage drops as positive. The interlink you will get to know in duality. Okay, in duality. Now, see, let me think of V1 is like this. Let me think of V2 is like this. Let me think of V3 is like this. Let me think of V4 is like this. Okay, now, if I consider this particular closed path, okay, let me give for this also V4, V5, V6, V7. Okay, now if I consider this closed path, if I start from here in any closed path, now minus to plus voltage rise, plus to minus voltage drop, minus to plus voltage rise, plus to minus voltage drop. Okay, now we can consider voltage rises equal to voltage drops, or algebraic sum of voltage rise equal to 0, or algebraic sum of voltage drops is going to be 0. We are going to consider algebraic sum of voltage drops in any closed path independent of the path followed is going to be 0. We are going to follow. Okay, because here one advantage will be there in applying KVL, because this is going to be very easy. It looks like very easy, obviously, right? While advancing in our problems, then if we follow this voltage drops equal to 0, it's actually very good. Means we may not do mistake. Okay, because in the exam pressure and all. But as per this only, I fixed the KCL as current leaving from the dot as from the node as positive. Okay, see here minus to plus. Okay, let me start from here. Okay, let me start minus to plus voltage rise. But I decided to take voltage drop as positive. So minus 2 plus V1 is voltage rise. Means from here to here, minus V1 is voltage drop only. No. So minus 2 plus voltage rise. But I thought of considering voltage drop. So minus V1. Now, plus to minus voltage drop only. Minus 2 plus voltage rise. Minus 2 plus voltage rise. So voltage drops I thought of taking positive. So minus V3. And plus to minus voltage drop is going to be 0. Got my point, right? Now, let us see the same equation again. Very simple. In applying the KVL in this, I touched minus first. In applying the KVL, I touched minus first. Minus, I touched plus, I touched minus, I touched plus. Sorry, it should be. It should be plus. I'm sorry, okay? Because it's voltage drop. See here, if you recheck the equation, minus I touched first, minus, plus I touched first, plus, minus I touched first, minus, plus I touched first, plus. This is going to be algebraic sum of voltage drops in a closed path equal to 0. We are going to consider. Okay. Now interlinking between this we will discuss later. Or we can think of writing for this closed path starting from V1. Now I touch minus first. So minus V1. After that I touch plus first. After that I touch plus first. After that I touch plus first. After that I touch minus first. Minus V7. After that I touch plus first. Plus V4 equal to 0. That's it. That's it. Okay. And again here, can we apply KVL for linear guess, non-linear guess, lumped parameter model? Yes. But distributed parameter model, kind of infinite system. Distributed parameter model is kind of infinite system. Distributed parameter model, can we apply? You can apply because it is basically will be derived from, basically KVL is derived from conservation of energy. So distributed parameter model also you can apply, but we cannot find closure paths there. Okay. Now, the moment it is derived from conservation of energy, for example, in future, some issues will come. Okay. Especially in some interviews, they will ask you, if we connect two voltage sources, of 10 volts and 5 volts, how much will be the net voltage across this? It is impossible to tell. Impossible, because minus 10 volts plus 5 volts, minus 10 plus 5 will not be 0. Meaning that conservation of, basically, it does not mean that Kirchhoff failed. Kirchhoff's voltage law failed. It means that conservation of energy failed. The moment conservation of energy is failed, conservative field concept is gone. So EM theory you cannot apply. The moment you cannot apply EM theory, what is network theory? Okay. So EM theory cannot be applied, meaning that network theory can never ever be applied. Now, meaning that for distributed parameter model, we can apply, everywhere we can apply KVL. Okay. With this, first section is over. Let me think of two-terminal system characteristics. Okay. Basically, by end of this discussion, we will come to know kind of in two-terminal system characteristics, our conclusion will be kind of our active elements. Our active elements will never ever be linear. But still, why we are using also, we have to understand. Right? First of all, we have to observe the diagram given by them. Okay. Normally, if they want to vary, they can vary. Okay. Plus minus voltage should be given, and current direction should be given. Okay. It means in the diagram you have to check whether voltage like this and current like this or not. For example, if current is in opposite direction, our complete analysis will be changed. The active will become passive, passive will become active. Okay. Anyway. Okay. And in this session only, you are going to come to know, okay, kind of how can BJT, FET and all, how can we call them as active also will come to know. Because what is meant by active? What is meant by active? Meaning that active element should be, as per our what they say, network standard, our active element should be able to convert from non-electrical to electrical. Non-electrical to electrical. But BJT or FET, transistor, means if you consider the transistor, is it developing any power from non-electrical power? Is it developing any electrical power from non-electrical power? No, it is not. But how can we call them as active? Also you will come to know. Okay. For example, I am taking this. Okay. So this is the characteristic given. Gradually we will increase the difficulty level, and gradually we are going to get the clarity from this also. Okay. Now, let us consider characteristic is given like this, and voltage is in this direction. Voltage is shown in this direction. Current is shown in this direction for this diagram. And at least they should mention passive sign convention is followed. Otherwise, actually some people are feeling that without this diagram, they are trying to explain this, which should not be. Okay, with this diagram, because if anything is changed, everything is going to be contradiction. Now, see here, we can decide about this, like 3 conclusions we can get. What are those 3 conclusions we can get? Maybe first thing is about linearity, we can decide linear or non-linear, and unilateral or bilateral, active or passive. These are the three conclusions we have to derive. And while defining this, maybe sometimes at starting I may not add few things, but while taking the class lecture, I'm going to add few other points. Then only you can understand it properly. Now, see here, what is meant by linear? What is meant by linear or non-linear? Already we know. In network theory, linearity is defined for only voltage and current. Voltage and current. Okay? And voltage and current. Voltage and current. Now, means that if I increase input by x times or k times, output also should be increased by k times. For example, if I think of voltage is the input and current is the output. Voltage is the input. For this input, current is going to be this much. For this voltage of V1, current is going to be I1. Now, if I double the voltage, current also will be doubled or not? Yes, obviously, because it is a continuous straight line going through origin. Okay, so the moment system characteristics is showing like it is a continuous straight line going through origin, meaning that obviously if you increase excitation input by x times or k times, automatically output also will be increased. So, in order to make a conclusion about linearity, okay, I understood. Okay, so in order to make a statement about linearity, we should check for the straight line, continuous straight line. What is meant by continuous straight line? You will come to know later in this session only. Linearity, meaning that characteristic should be continuous straight line. Should be continuous straight line going through origin. Make a note of it. Okay, let me underline continuous. About this we'll discuss later. Now, coming to the second point, what is unilateral, bilateral? And one more interview question. Okay, means to one of my student, IIT Delhi guys asked this question. What is the difference between bilateral and reciprocative? Okay, because reciprocity theorem, bilateral is about reciprocity theorem. Right? If excitation is if excitation is there, response is there, input is there, output is there. If I exchange, ratio should be maintained. Okay, meaning that is bilateral. But in IIT Delhi interview to one of my students, of course, I think some time back, they asked what is the difference between bilateral and non-reciprocal. Both are same. But as per one of the professor in one of the IIT, he said that if we have only two elements or two terminals, first terminal, second terminal. Okay, so this is two terminal. For two terminal system, we have to use unilateral or bilateral. For three terminal, kind of transistor, for example. Okay, for three terminal, we have to use the term of reciprocal or non-reciprocal. He shared that. Okay, so see here, of course, this is kind of, okay, sometimes the moment that they ask you any question, you should have the answer. Otherwise, there is no logic behind this. Okay, see here, for this, equivalent is going to be unilateral, meaning that non-reciprocal slash reciprocal. Okay, for two terminal, kind of diode. Diode we can call it as unilateral. Resistor we can call it as bilateral. Okay, but BJT or SCR, okay, or FET are kind of magnetically coupled networks, are kind of two-port networks. Now, two-port networks are going to have input port, output port. So total 4 terminals we are going to have. Magnetically coupled also minimum 4 terminals we are going to have. And BJT, FET, SCR and all 3 terminals we are going to have. So the moment more than 2 terminals, we have to use reciprocal or non-reciprocal, it seems, as per him. Okay. Now, see here, next thing is going to be unilateral, bilateral. Okay. So unilateral, bilateral, how to decide? See, what is meant by unilateral? Okay. See here, if I think of voltage is the input, current is the output. Voltage is the input, current is the output. Even if I interchange excitation to response. Okay. Excitation will be there, input will be there, response will be there. Even if you interchange excitation to response, then also ratio of response to excitation, which is nothing but transfer function. Ratio of response, output to input. Ratio of response to excitation should be maintained constant or should be invariant. Is nothing but this. Meaning that, see here, if I apply okay, now for example, if I apply V1 here, current is going to be I1. Now if I interchange, okay, this is plus V1, no, let me think of minus V1. If you reverse, automatically current also should be reversed. Is it going to happen or not? Yes. Why it is happening? Because my characteristic is symmetric between first and third quadrants, or the same thing will be there between second and fourth quadrants also. Okay. For example, if I have red characteristic, then what is going to happen? For this much V1, okay, let me take here, this much Vx input minus Ix, because this is negative side of current, no? So minus Ix is going to be the output. If I convert that into minus Vx to minus Vx, minus Ix is going to become plus Ix. Ratio is maintained, right? So point here is very simple. If our characteristic is symmetric, between first and third quadrants, or second and fourth quadrants, it should be reflected. Okay. So in this particular condition, is it unilateral or bilateral? It is bilateral. About that only we are discussing. Okay. So let me think of bilateral. What is meant by bilateral? Meaning that characteristic should be symmetric between first and third, or second and fourth quadrants. Fourth quadrants. Okay, this is over. Now let us think of active passive. Of course, for this directly many people know that okay, this is a passive and all. Okay, but we are going to extend this discussion, right? Now let us think of active passive. This is very crucial because many guys will be confused here only in the next problem, in the next example. Now let us think of if my operating point is here in this particular system. Okay, this particular system is being operated at this operating point. Then what is going to happen at this operating point? Voltage magnitude is positive, current magnitude is positive because this is 0, 0. So this is positive Y, this is positive E, first quadrant. So voltage at this point, voltage magnitude is positive, current magnitude is positive. Voltage magnitude is positive, current magnitude is positive. So voltage multiplied by current is going to be positive. Meaning that by passive sign convention, that's why sign convention is important. Sign convention is given in such a way that for positive voltage, positive current magnitude, of positive voltage magnitude and positive current magnitude, it is going to absorb power. Okay. For example, because this is one of the ESC question. Okay. And in that they have given this. But for example, if they have shown in your exam I in opposite direction. Okay, if they have shown in your examination I is in opposite direction, then what is going to happen? Means, for example, I direction is changed. I direction is changed in your examination in the diagram given in the exam. Then what is going to be? Voltage magnitude is going to be positive. Same characteristic they might have given. Voltage magnitude is positive, current magnitude is negative. Meaning that voltage magnitude is positive, current is shown in opposite direction. No, so current direction is going to be positive, meaning that it is going to deliver power for the same characteristic. You understand my point, right? So simple. First of all, we have to focus on here. Okay. Anyway, passive sign convention is followed here. Okay. Then, whenever voltage magnitude is positive, current magnitude is positive. Voltage magnitude is positive, current magnitude is positive. Meaning that whenever this is positive, net power absorbed is going to be positive because current is entering into the positive terminal of the voltage. Now, maybe if it is operating at this point. Then this is current only, so current magnitude is negative, voltage magnitude is negative. So this is going to be negative voltage, this is going to be negative current. Again, V into I is going to be negative multiplied by negative is going to be positive, which is absorbing power. What does it mean? Basically, it's a passive element because means at any operating point, if you see, it is going to absorb power, but this has to be changed. This particular explanation has to be changed. Very soon I'm going to change that. Passive, meaning that characteristic should be in first and third quadrants only. And I'm going to add a few more words for this at the end of this session. Okay. So ultimately, what is this characteristic? Let me conclude, and after that we are going to take the next thing. Okay. So this characteristic is going to be straight line going through origin. Continuous straight line going through origin. So it should be linear. Characteristic is between first and third quadrants. Okay. Characteristic is between first and third quadrants, and it is symmetric. Reflected to each other. So it should be bilateral. Yes. Okay. And what is one more? It should be passive because at any operating point, it is absorbing power only. Right? Now, let us take again, this diagram is important. Okay, this has to be followed, right? Now, for this diagram, let us suppose characteristic given is like this. Now you will get the clarity about active element, because active element already we defined active element, but at that time you might not have heard it properly. Now you are going to get better clarity about it. Okay. Now characteristic given. Characteristic given is this. Now let us see. First of all, let us start with active passive. Now, if you see here, let me consider this particular point. Okay. I'm sorry, I have to show voltage here. I have to show current here. Right? Now, if I see my operating point is here, meaning that here voltage magnitude is positive, current magnitude is positive multiplied by positive is positive, and the passive sign convention is followed. So if operating point is here, it is actually absorbing power. Right? Now, if it is operating here, then means my voltage magnitude, positive voltage here, negative voltage here. So voltage magnitude is going to be negative, and the current magnitude is going to be negative. Meaning that again negative multiplied by negative is going to be positive. Passive sign convention is followed. Okay, so power is going to be absorbed. Now, if the operating point is here, power will be absorbed. If the operating point is here, power will be absorbed. And if the operating point is here, then if the operating point is here, voltage magnitude is positive. but current magnitude is negative. Current magnitude is negative. So if you operate at this point, meaning that voltage multiplied by current is going to be negative. Voltage multiplied by current is going to be negative. Meaning that the absorbed power, say passive sign convention, the absorbed power is going to be negative. Meaning that it is actually delivering power. Now, what should we say? Is it active or passive? Can I say that whenever I'm operating here, it is passive, whenever I'm operating here, it is passive, and whenever I'm operating here, can I say it is active? Right? But for this particular system, I have to say only one thing, active or passive. What should be said? Active. Because let me think of the example I have taken in our previous sessions while defining or while explaining active elements. This is 10 volts. This is 5 ohm. This is 5 ohm. Then how current will flow? Current will flow in this direction, 10 minus 5 by 5, 1 ampere. And it is actually delivering power, 10 into 1, 10 watt. It is actually absorbing power, 5 into 1, 5 watt. Now can I say this particular element, can I say this particular source is passive? In this particular system, in this particular configuration, it might be absorbing power, but it is having the ability to deliver power. I repeat, it is having the ability, because if you disconnect with this particular network and if you add to another resistance, from after disconnecting here, if I add with another resistance, it is having the ability to deliver power. But you are not utilizing that. Ultimately, it is having the ability, it can deliver, it is having the ability to deliver, meaning that it is active. Now, let us think of this. If you think of this, here, see here means, of course, at this point it is absorbing, at this point, but it is having the ability to deliver. Maybe without utilizing its ability, you might operate here or you might operate here, but ultimately it should be active only, right? So here it is going to be active. It is going to be active. Okay. So conclusion is this particular characteristic will make the element or will make the system as active. Problem solved. Now, let us think of linearity. Okay. For example, if V is the input and I is the output. If V is the input, I is the output. Okay. If I double V, will I be doubled? No. For y equal to mx, it is okay, but not for y equal to mx plus c. Okay. So for this voltage, this is the current. If I double the voltage, current will not be doubled. It will be decided by the slope and all. You are getting my point, right? So point here is, it is going to become non-linear, because if you increase excitation by k times, response will not be increased by k times. Okay. So it is going to be non-linear. And third thing is, unilateral or bilateral, we have to decide. Okay. Unilateral, bilateral in the sense, if you change the polarity of the voltage, current polarity has to be changed by the same magnitude, because response to excitation, transfer function should be invariant. Okay. Let me think of applying this much voltage for this much current. If I negate this, okay, if input voltage is this much, current is going to be this much. If I negate the voltage, current is going to be negated, but not the same magnitude, right? So it is going to be unilateral. Okay. Now let us think of one more. Okay. I'm not drawing every time that particular circuit. Passive sign convention is assumed. Now let us think of Gradually, I'm increasing the kind of complexity such that you will get better understanding now. Okay, that is the characteristic. A kind of UJT, but not really. Okay, this kind of characteristics. And here, again, it is current and it is voltage. For time being, let me draw. Now, fatapat, let us start. Is this characteristic linear or not? Obviously not linear because it is not a continuous straight line going through origin. It is not a continuous straight line going through origin. So obviously it will be non-linear. Because if you increase input by k times, output will not be increased by k times. Okay. Now, is it active or passive? Means in the first quadrant, we will discuss about it later. In the first quadrant, we will discuss about it. Means immediately after this, we are going to discuss. But if you think of, it is there in the second quadrant. No? So the moment it is touching the second quadrant, for positive voltage, negative current is coming. See here, for positive voltage, negative current is coming. Negative current is coming, right? For positive voltage, negative current is coming, meaning that it is going to absorb negative power, it is delivering power, so it should be active. Okay, so this is active. Okay, now only I am going to add, I told you, no, some few words I am going to add to the explanation of active. We are going to do that now. Okay, non-linear, active, and unilateral, bilateral. Obviously unilateral because first and third symmetry should be there. Second and fourth symmetry should be there. So it is asymmetric. Reflection is not there. So it is going to be unilateral. Okay. Now, okay, let me take the same. Let me move to 0. Okay, so this characteristic now is not from left side. It is from only in the, it is there in the first quadrant only, let us see. Okay, again let us try to analyze. Again try to analyze. Now, let us start with unilateral or bilateral. It is unilateral because first and third symmetry should be there, and second and fourth symmetry should be there. First quadrant only some characteristic is there. So obviously it is unilateral. Okay, and after that we will see active passive later. Okay, and one more thing. Non-linear. Okay, obviously is it non-linear or not? Yes, because characteristic is not a straight line going through origin, so it is going to be non-linear. Now let us think of active. Is it active or passive? Maybe you may think that characteristic is there in the first quadrant only. So voltage multiplied by current is going to be, voltage is positive, current is positive. So voltage multiplied by current is going to be positive. So it is going to absorb positive power. It is going to absorb positive power. So it should be passive. No, no. It is active. It is active. Why it is active? See. If you see in that area, is it having slope negative or not? For example, from here to here, from here to here, this is going to have what they say positive slope, meaning that means we can represent this with positive resistance. But here, from here to here, it is showing negative resistance region. Yes, as oscillator, if you want to use, we are going to use in between these two operating points only. Anyway, like the moment you have negative resistance, slope is negative resistance, obviously it is going to deliver power. Okay, so it is called as active. Now, let us think of adding the same. It is having negative slope. Whenever, even though characteristic is there in the first and third quadrants, but if you find a negative slope, it will become active. See, characteristic should be in first and third quadrants only, that too with positive slope. That too that too with positive slope. Okay, you have to make extra statement of this. What about zero slope? Positive slope is fine. Negative slope is fine because negative slope, negative resistance region and all. But let us think of zero slope. Okay, if I think of zero slope, okay, again voltage, current, op amp open loop characteristics if I consider. Now you will get the clarity about BJTs and all. Okay. Now this characteristic also, if you see, good. Now if you see this particular characteristic, means from here to here, kind of positive resistance is there, but from here to here, slope is going to be zero. The moment slope is going to zero, forget about all. Let us think of how to model this particular characteristic by using our basic properties. If I want to focus in between this area only, okay, my focus is in between this area, and in this particular complete characteristic, I want to model the characteristic of this particular range only. What has to be done here? Voltage is going to be constant, independent of current. Voltage is going to, means in this particular area, voltage is going to be constant independent of current. Voltage is constant independent of current. So we have to model that way. Zero slope. Voltage source. Okay, current of this particular value. Because from here to here, current can vary, but voltage is going to be constant. So the moment you have zero slope, there is no other way. We have to model that way. Either voltage source or current source, depending on the thing here. Okay, so point here is simple. In this particular region, I have to model that with voltage source only. Okay, so positive slope means, see here characteristic is there in the first and third quadrants only, but with zero slope it is going to be active. With negative slope it is going to be active. With positive slope it is going to be passive. Okay, now let us conclude this. See here, this characteristic, is it linear or non-linear? It is not a continuous straight line going through origin. So obviously it should be non-linear, right? Because if I take this much voltage, and for that some current is there. If I increase voltage by 10 times, current will it increase by 10 times? Okay, non-linear, no. Unilateral or bilateral? It will be bilateral because first and third quadrants, if you see, means my waveform, my characteristic is symmetric. So it will be bilateral. We will discuss about our active elements also soon, just wait. Okay. Now, let us think of active passive. Meaning that from here to here, active only, obviously, so active. Okay. Conclusion is very simple. Even though characteristic is there in the first and third quadrants only, but still, if it is having zero slope, or if it is having negative slope, it will become active. If it is having positive slope, where is this? Like this. If it is having characteristic is there in the first and third quadrants only, but with positive slope, it will become passive. Okay. Now, if you think of FET, BJT, or whatever it may be, okay, means much discussion is there. Okay. Now, if you think of BJT, is it amplifying the power? Is it consuming non-electrical power in order to transform it into electrical form of power? No. In that case, how can you call them as active? In analog electronics, analog faculty say that BJT is active, FET is active. Okay, and of course, if you think of maybe combinatorial characteristics of our BJT, okay, in this region only it is supposed to be operating as an amplifier. Okay, in this region only, better. Okay, the operating point is supposed to be operating, then only it will behave like a amplifier. But anyway, zero slope. Okay, but anyway, point here is very simple. Even though it operates in this region, how can you consider it as a active element? Because as per our network theory, active element means that which should convert from non-electrical form to electrical form is what do you say, active element. Right? Here, there are two things. First thing is, it is taking signal in electrical signal. It is taking base power. Okay, biasing power. Sorry, not base power, biasing power. Okay, so my BJT is going to take biasing power and signal power by drawing the from the biasing circuit, by drawing the electrical power only, it is amplifying the signal to amplified level, more level. Okay, so if you think of BJT, if you consider electrical signal input and also bias power plus signal power is going to be net output power. Okay, but how can you say it as an active? By not considering bias power. Okay, whatever may be the power supplied by the biasing circuit, if you neglect, then input signal is this much, output signal is this much. Signal is getting amplified. So we are going to consider them as active by not considering biasing circuit, by not considering power supplied by biasing circuit. Okay. Anyway, coming to the next thing. Next, let us take one more example. If the circuit is given like this, as usual, this is voltage and this is current, and passive sign convention is followed. Now, if you can conclude this discussion can be left. Okay. Now, see here, let us think of first of all linearity. Okay. So for this much input, this is the output. If I double the input, output is going to be doubled. Okay. For positive voltage, negative current it is given, but direct proportionality is there. Okay. Because it's a continuous straight line going through origin. So this system is going to be linear. Now, let us think of what they say active passive. Obviously, it should be active because wherever the operating point you take, okay. So wherever the operating point you take, voltage is positive, current is negative. Voltage magnitude is positive, current magnitude is negative. Meaning that at this operating point, voltage is positive magnitude, current is having negative magnitude. So voltage multiplied by current power is going to be negative. So it will become active. It will deliver power. Here also it will deliver power. Okay. Now lay over that. So it is going to be active. Now next point is it unilateral or bilateral? Okay. Two terminal. No, I can use unilateral, bilateral. For three terminal. In two-port networks and all, we use reciprocal or non-reciprocal. Okay. Now, bilateral, for example, for this much input, this is the output. If voltage is reversed, polarities are reversed, current is going to be reversed. If magnitude of voltage is reversed, current is going to be reversed by the same. Because it's a continuous straight line, so it will become bilateral. Because we discussed it clearly. Okay, bilateral meaning that characteristics should be symmetric between first and third or second and fourth. Okay, if you think of linear, it should be continuous straight line going through origin, means independent of first, third or second, fourth, it doesn't matter. And active, if the characteristic is touching the points of either second quadrant or fourth quadrant, automatically it will become active. Even though characteristic is there in the first and third quadrants only, then also it may become active because we have to observe the what they say, slope of the characteristic. Okay. Thank you very much, and meet you in the next session. Kindly subscribe to our channel Gate Conqueror, share the session, okay, because it will be useful to someone. Thank you guys. Thank you very much.